The matrix exponential is separately a solution for the system. Any questions?
I haven't seen the matrix exponential.
You have not seen the matrix exponential before, right? So, obvious question. What are you talking about, matrix exponential? How do you even do that? How can you take an infinite series of matrices? Well, you should prove that. And we'll talk more about this maybe next class, perhaps. Yeah, because next class I'm supposed to change to start talking about geometry, right? So maybe I can start talking about analysis when we start talking about geometry. Maybe I'll kind of start sliding into the advanced calculus more next time. But we can give a rigorous meaning to the convergence of a matrix sum series. And you can prove that this series converges for any matrix. And you can prove that you can do term-by-term calculus on such a power series. So we can justify all these steps. This converges for any matrix. But admittedly, you're like, well, that's lovely, but it seems like you've just given me a description of the solution which is like computationally impossible, right? Because it's enough trouble to calculate the square of a matrix. It's even more trouble to calculate the cube of a matrix, to calculate the fourth power of a matrix, the fifth power, the seventh power, the nth power. Generally, that's a really cumbersome thing. So it's lovely that you've given me this matrix exponential solution, but what good does it do me? Because it's very formidable calculation to actually calculate the columns in this thing. Now, I should mention, we can prove that the determinant of the matrix exponential is actually equal to the exponential of the trace of A. So it's not equal to 0. Or more to the point, you can prove that EA is invertible, and its inverse is just this. So it is an invertible matrix of functions. I should put T's here for any time. It is an invertible matrix of functions. So once you come to terms with its existence, all right, once you come to terms with its existence, it's an invertible matrix. It is a fundamental solution matrix to the problem, which means that if I can just figure out a way to calculate columns in the matrix exponential, man, we'd have it. Generalized eigenvectors do that. We can calculate columns in the matrix exponential by hitting it with generalized eigenvectors. The way this is done, in my view, is through applying what I like to call the magic formula. You say, the magic formula? What do you mean? Well, let me show you. So, the basic idea here is that the generalized eigenvectors, we want to make use of that data. So we want to change the formula for the matrix exponential so that it respects the chain condition. And if we can do that, then everything just falls into place. So let me show you. So here it goes. E to the TA is equal to e to the t times a minus lambda I plus lambda I. So I first of all add 0. All right. Next, I use a property of the matrix exponential, which probably you should work out and understand more. But I'm just gonna, we're just gonna have to leave some of those details on the table here. All right. But that's a property of matrix x. Now I should warn, the matrix exponential does not obey the laws of exponents, generally speaking. There's a more complicated relation. It actually involves a series of nested commutators. It's something called the Baker-Campbell-Hausdorff relation. We'll talk more about that some other day. The point is, this is true because that's the identity matrix, and that identity matrix commutes with all matrices. So like, you can show that e to the a times e to the b is equal to e to the a plus b if you're given that ab is equal to ba. Like, if you know that, it is true that the law of exponents holds for the matrix exponential. And because lambda times IT is a scalar multiple of the identity matrix, that commutes with everything. And then it turns out that that is exactly equal to e to the lambda t times the identity matrix. So we can just say that times this matrix. That, I can demystify. Let me just talk about that for the 2 by 2 case, just so it's a little bit less mysterious. If I have this lambda t, like this 2 by 2 matrix, well, that's the sum, n equals 0 to infinity of this matrix. But that's exactly lambda, when we look at it, that's really this. See, that's not helping. I'm sorry. This works out to e to the lambda t, e to the lambda t. Because when you take the powers of the lambda t, the diagonal matrix, the power of a diagonal matrix is a diagonal matrix of the powers of the diagonal. So that allows you to trade the exponential series for the matrix for the regular calculus 2 series of the components of the matrix on the diagonal, which gives us this calculation. But what that means is that this is e to the lambda t times the identity matrix, which means that I can just replace this with e to the lambda t here. And I could put the identity matrix here, but why bother? Then what? Well then, this is e to the lambda t times the identity plus t times a minus lambda I plus, well, t squared over 2, a minus lambda I squared plus dot 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 dot. I mean, this is a series, it goes on and on. This is what I lovingly refer to as the magic formula. Because that is what allows us to extract solutions. So like, going back to my example from last class, right? Going back to my example from last class, remember what we did? We didn't have the third solution, right? I'm gonna go and derive that third solution right now with this, okay? So, let me remind you. Oh, so right there it is. See that? Right here. Okay. So my claim. So think about this. If you do e to the ta times a constant vector, this is equal to a linear combination of columns of e to the ta, right? But we're talking about a linear differential equation. The sum of solutions is a solution. So that means that any matrix column product of a solution matrix is a solution. So in some sense, I give up on calculating the columns of the matrix exponential, and I just allow myself to look for linear combinations of the columns which are of interest. Okay, so let's do it. So we have e to the ta times u, right? So that's e to the, what was my eigenvalue? It was 2, wasn't it? Yeah, 2. E to the 2t times the identity matrix plus t times a minus 2i plus t squared over 2, a minus 2i squared plus dot 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 u, right? Now what happens? We get, well, first of all, one of the things I seem to have lost, but we proved last time, was that a minus 2i squared on u equals to what? Maybe you can see it better today since we've done more calculations. If I subtract 2 times the identity from this is my A matrix, right? if I take 2 times identity minus that, right? And I square it, I end up, that piece goes away, goes to 0, right? So my u vector was this. So like u vector explicitly was 0, 0, 1, right? That's what we figured, that's what we come to. But it is a generalized eigenvector of order 2, which means that, what? It means that this all goes to 0. So yes, we've got an infinite series, but you know what? It truncates because the general eigenvector, and eigenvector is designed to do that. And so you're just left with these two terms, right? And what you got then is e to the 2t times u vector plus t times what? Well, what's a minus 2i times u? It's equal to e2. So explicitly, this is e to the 2t. The vector u was actually 0, 0, 1. And then we've got t times 0, 1, 0. So the third solution that I was supposed to put up into here, we couldn't find it with eigenvectors, but now we've got it. C3, I'm going to put it over here, plus C3, what? E to the 2t times what? You see it? 0, t, and 1. That is the general solution to this system of differential equations. So that's it. To finish the solution to the differential equation, what we do is we use the generalized eigenvectors and multiply them across this formula. If you had a generalized eigenvector of order 3, if you had order 3, then the way this works out would be like e to the 2t, well, e to the lambda t, let's say, times u, let me say order 3. It'd be u3 plus t times u1, u2, plus t squared over 2 times u1. If we had, a minus lambda I, u3 equals to u2, a minus lambda I, u2 equals to u1, a minus lambda I, u1 equals to 0. So if you had like a generalized eigenvector of order 3 for your matrix, that will generate a solution like this. So I know you haven't had differential equations, but when you study differential equations, one of the things you find out is that the solution to the constant coefficient problem, it usually is solved with exponentials or sines and cosines, but every so often you get a repeated root. And in the repeated root solution, all of a sudden you get multiplication by t. And that has to also happen here somehow. But it's not just multiplication of the whole solution by t. This is what students do in differential equations when I cover this, is they just multiply the whole thing by t, because they think it's the same as like the nth order problem. But it's not. The way the t appears, it's a little bit nuanced. But we can get t times an exponential, or even t squared times an exponential in our solutions if there is a generalized eigenvector of order 3 for the matrix. Now the way sine and cosine enters in is if you have a complex eigenvector. Because if you have a complex eigenvector, you get a complex exponential. Complex exponential, which then gives you like real exponentials times sines and cosines of the imaginary part of your eigenvalue. And so you get these interesting linear combinations of exponentials times sines and cosines. And if your system was like the one I just erased, like up here, that would give you a system that actually had solutions that had like t times cosine or t times sine, all times like e to the lambda t. So we can look at an example or two maybe next time if you want to see more. So should I just take the next class? Well, I don't know. I'm kind of debating how much differential equations I should show you. I can say much about differential equations if I'm left to my devices, but I think this is a good place for us to stop today. So. Mm-hmm.